Welcome back to Logic 101. I'm William Spaniel, and this lecture is on double negation. We're actually kicking off our unit on replacement rules, so let's start things off by briefly talking about what this unit is supposed to do. As it turns out, some logical expressions have multiple identical representations. So you can write one logical expression in one way and write that same logical expression and maintain the same meaning in a different way. However, some of these representations are more useful than others because they are simpler. So you can look at one of these expressions, know exactly what it means, and look at another one of these expressions and have no idea what it means, even though they mean the exact same thing. And what replacement rules allow us to do is interchange these expressions as we please. So if we don't like that really complicated version of it, we can get rid of it and replace it with a simpler version that we more intuitively understand. So replacement rules are very useful at keeping things simple for ourselves. And to start things off, let's look at the simplest of replacement rules, the double negation. So this is true. P is true if and only if not P is true. This is very simple. Think about this mathematically. Think about this algebraically. Imagine P was a variable, the negations were negative signs, and the biconditional was an equal sign. Well, this would be like saying variable P is equal to the negative value of that variable P. You just get rid of those two negations, and it becomes the same thing as it was before. So this is very simple and it's very straightforward. It's identical to what you think of as double negation in mathematics. And we can actually verify that this statement holds by looking at a truth table. Yeah, those truth tables just never leave us. So let's look at that truth table. So we have one simple expression here. It's just a P. Now, as it turns out, double negation and all these replacement rules will work regardless of whether we're looking at simple sentences or compound sentences. So actually this works if P is also a compound sentence. It doesn't have to be a simple sentence here. But nevertheless, let's go forward. So we have the second column, we have the negation of P. So if we flip the original truth values of the first column, we get false and true. And then in the third column, we take the negation of the second column, which means we flip those things around again. And you'll notice here that we are exactly where we started. In the first row, not P is true, just like P. And in the second row, not P is false, just like P. And so for the rest of this, it's going to be very straightforward. Let's take a look at the fourth column here. We have P implies not P. So in the first row, that's true because both of those are true. And in the second row, it's true because we have vacuous truth as a result of P being false. So that holds true, just like that. And then in the fifth column, not P implies P. Well, in the first row, both of those things are true. And in the second row, not P is false. So we have vacuous truthfulness there. And so we get true. And then if you take the conjunction of columns 4 and 5, essentially conjoining the two implications, that's what the biconditional is. Well, it's always true in both of those columns, so we get always true in the last column. So what that is saying here is that P is in fact equal to not P. And going forward, when we're doing this, I'm going to cut out these extra steps of looking at the biconditional and looking at two implications and combining it into that biconditional. So in the future, we're only going to be looking at these simpler steps. I'm just going to compare one column to another column. And as long as it's the case that the rows are identical for two columns, that means you can interchange the original value in those two columns as you see fit. So P can be replaced by not P and vice versa. I've hinted before why this is really cool and useful, but just to recap that, not P is an awfully bulky expression. And replacement rules mean that we never ever have to use an expression like not P again. If we see something like not P, we can erase it and we can just replace it with P, and we're not damaging our logical argument. There is no logical difference between not P and P. So that's a simple replacement rule. And what we're going to be doing now is looking at more complicated, more interesting replacement rules and teach you a little bit about how there's logical equivalence among multiple different expressions. Hope you enjoy this, and I'll see you next time. Take care.